All right, so in class, we did some review with our exponent rules at the beginning of class, but then we moved on to graphing our exponentials. So this unit comes with exponent rules and then graphing exponential functions. When we're talking about an exponential function, the goal right now is to kind of get a sense of what an exponential function looks like and some general behaviors of an exponential function. So the parent function of the graph is a times b to the x. So this looks a little different from our normal parent functions because there are some variables in here that are going to change and fluctuate. But note that b is a real number greater than 0 except 1. In some cases is a real number greater than 0 but is not 1. So that means it can be a fraction, and we'll look at what that looks like here in a little bit. So this first one, all we're going to do is we're going to take this parent function or take this exponential function and kind of plug in the x values and solve for y. So here I have 2 to the x, so if I want to make x negative 2, I would have 2 to the negative 2. So then if we remember our exponential or our exponent rules, when we have a negative exponent, we move it or we make it reciprocal. So we'd put it underneath a 1 and move it to the bottom of the fraction. So then 2 to the second power would be 4. So when x was negative 2, my y value was 1/4. And we're going to repeat this. So if I do this to the negative 1, again, to make our exponent positive, we move it or we take its reciprocal. And then 2 to the first power is just 2, so this becomes 1/2. From our exponent rules, we should remember anything to the 0 power is just 1. 2 to the first means 2 one time, so 2, and then 2 to the second means 2 times 2, which is 4. So we plug in these x values to find their y values, and then we're going to sketch this graph. So if I have negative 2 and 1/4, so that's just a little bit above 0. Negative 1 and 1/2, so that's a little bit bigger. 0, 1, 1, 2, and 2, 4. And what that does is that's going to make us a graph that looks like this. A couple things to note is that this graph is never going to cross our x-axis. So this also has a horizontal asymptote of y equals 0. If we remember our horizontal asymptotes from our rationals unit. And so we'll talk about this a little bit here. So the shape of our graph, we have a curve. Right now we're looking at a graph that's called exponential growth. As we go from left to right, we're going upward. Right, our graph is growing. So as we move from left to right, our graph is growing towards infinity. So then it says, does the graph intersect the x-axis? Explain how you know. No, we have a horizontal asymptote. That's at y equals 0. You can also think of this as, this would mean that you get a y value of 0. So if you have 2 to the x power and you want that to equal 0, remember we already said that 2 to the 0 power was 1. And then every other value that we've plugged in, every other integer we plugged in gave us a value other than 0. So there's no way with our exponent to get a value of 0, which is why we have this asymptote. There's no way to cross that line because there's no way with an exponential that we can get a y value of 0. So that's why we know this horizontal asymptote is at y equals 0. So then if we think about its domain and range, we think about our x values first, so our domain. Our graph is going to the left forever and to the right forever. So right, this graph is going to keep going this way and going up this way. So it's going to use all of our x values. So our domain will be negative infinity to infinity, which is going to be true for all of our exponentials. And then for our range, Remember, we just said that we have an asymptote at 0, and we also stated that it will never get a y value of 0. So since we're talking about our range being our y values, our graph is heading towards 0, and the farther you go to the left, the closer and closer it's going to get to 0. It's just never going to touch it. So our range is going to be 0 with a parentheses. Remember, we used to use parentheses or brackets, but here we're going to have a parentheses, and then it's going to go up forever going this way. So it's going to use all of our positive y values, meaning it's going towards infinity. All right, so let's just look at our next one. So you can see our exponential is the same 2 to the x, but now we're multiplying this by 3. And so what that's going to do is it's going to create a stretch in our graph, and we'll look at that here as we do this. So when I plug in my x value, so I have 3 times 2 to the negative 2. Well, we already knew, remember, order of operations tells us to do exponents before we multiply. So if I was to solve this first, we already know from the top of here, 2 to the negative 2 is 1/4. So now I have 3 times 1/4, which would just give me, when I multiply these fractions, I multiply straight across. So 3 times 1 is 3, 1 times 4 is 4, so it'll give me 3/4. So then if I do 3 times 2 to the negative 1, remember we already solved 2 to the negative 1 up here. That was 1/2. So now I have 3 times 1/2, which again, when we're multiplying fractions, we would put a 1 underneath to make that a fraction and then multiply straight across. So 3 times 1 is 3, 1 times 2 is 2. So I have 3 over 2, which I could also write as 1.5. If you want it as a mixed number, I will accept either. Then 3 times 2 to the 0. Remember, 2 to the 0 became 1, so 3 times 1 would just give me 3. Then I have 3 times 2 to the 1. 2 to the first power is 2, so then 3 times 2 is 6. And then 2 to the second power would give me 4, so 3 times 4 would give me 12. So really all I did was take these initial values and multiply them all by 3. And so what we'll see that does to our graph, right? This negative 1 is now past 1, 0, 3, 1, 6, and then 2, 12 is really not even going to fit. It's going to be somewhere up there. So what happened to the graph with the stretch is it just kind of became steeper. It grew more quickly. We started going up a lot faster with that 3 in the front. So that stretch, that 3 in the front, that stretch by 3, made our graph increase more quickly. The domain and range would still be the same. The asymptote, when it stretches, doesn't move. If you think about 0 times 3 would be 0 anyway. So the asymptote didn't change, right? This part of my graph is still trying to get closer and closer to 0, but never cross it. And I'm still going on in my x values from negative infinity to infinity. So it didn't really change the domain and the range in some of our parts of our graphs. It really just made that graph stretch out and increase quicker. All right, so then if we look at the back, now we're looking at 1/2 to the x power. So we're going to kind of do the same general thing we did on the front. We're going to plug in these x values, kind of complete our table, and then make the general sketch of our graph. So if I do 1/2 to the negative 2 power, because it's a negative exponent, we would want to make it positive, which means we would flip our fraction over. You could think of this as 1 to the negative 2 over 2 to the negative 2. So when I distributed that negative 2 on the outside, which would then, to make them positive, I would want to flip them over. So then 2 squared would give me 4. 1 squared would give me 1. 4 over 1 would just give me 4. So that negative exponent is going to then flip that fraction over. 1/2 to the negative 1 power, again, flips my fraction over. So I'd have 2 to the negative, or 2 to the positive 1, which would just give me 2. Still anything to the 0 power, including fractions, would be 1. Then 1/2 to the first power would just stay 1/2. And 1/2 to the second power means 1 squared over 2 squared. 1 times 1 is 1, 2 times 2 is 4, so I end up with 1/4. So when I graph that, I have -2, 4, -1, 2, 0, 1, -1.5, or 1.5, 2, 1/4. So it's generally the exact same graph, it's just going the other direction. So it's the same looking curve, but now this is called exponential decay. And it's exponential decay because now my graph is going down, right? It's getting smaller when we go left to right. It's getting, my y values are getting smaller and smaller and smaller and smaller. My graph still does not cross the y-axis. We still have a horizontal asymptote at y equals 0. Right? There's still an asymptote here that my graph is not going to cross. Even as a fraction, there is no way to make an exponential equal 0. As a straight exponential, when we start looking at transformations, we may see some that cross the y-axis, but it won't be, but that'll be because the asymptote moved as well. So just keep that in mind. And then my domain and range actually did not change. My graph is still going in both directions for my x values. I can still use any and all x values. And now, though my range and my graph is going the other directions, it's now decaying instead of growing. It still is getting closer and closer to 0, but never touching it. It's on the other side of my graph, but it's still going from 0 and then using all of the y values above that. So from 0 to infinity. Remember, we always write it from least to greatest. So even though we're kind of thinking about this side being infinity to 0, we always write our domain and range from least to greatest so that 0 would still come first. So then if we look here, same idea. Again, we're multiplying by that value of 3, so that means we're stretching our graph. So if we take all of our initial values from the top, right, I know 3 times 1/2 to the -2. Well, I knew this part, 1/2 to the -2, was 4. So I have 3 times 4, which would give me 12. 3 times 1/2 to the -1 power is 3 times 2, which gives me 6. 3 times 1/2 to the 0 power. Anything to the 0 power is 1, so then 3 times 1 is 3. 3 to the 1/2 would give me 3/2, which we know as 1.5. And then 3 times 1/2 to the second power is 3 times a fourth, which gives me 3/4. Yeah, so all we did was take these x values from this first one, or the y values from this first one, and we solved those first. That's what we got first when we did our exponent, and we just multiplied all those values by 3. So -212 won't really fit on our graph, but then I have -1, 6, 0, 3, -1 and, or +1 and 1.5, and 2 3/4. So now, again, it's the general same shape of the graph. It's just decreasing more quickly. That stretch makes it a little bit steeper. You'll also notice that here, this initial value of 0, 1 is now at 0, 3 because it got stretched by 3. So as we do some graphing on our own, that value 0, 1 will really come into effect as we look at our transformations. But stretching also affects that kind of initial value that we look at. So now this graph is stretched by 3. And then our difference between our first two graphs on the first page, right? If we look at these two graphs, the difference between these two graphs is these are exponential growth because they're moving up, while these two graphs are exponential decay because they're going down. So graphs 1 and 2 were exponential growth. And that comes from, if we're wondering where that comes from, if we compare our two graphs, right? This was y equals 2 to the x, or 3 times 2 to the x. It's really that value that we're raising to the x power. That b value, that is our exponential growth. So when b is greater than 1, we have exponential growth. For instance, that y equals 2 to the x, or y equals 3 times 2 to the x. And then if b is always greater than 0, but less than 1, so if b is between 0 and 1, meaning that it's some sort of fraction less than 1, then we have exponential decay. So what we saw from graphs 3 and 4 were our exponential decay. So y equals 1/2 to the x power, or y equals 3 times 1/2 to the x power, right? That b value being a fraction less than 1 gives us exponential decay, and that's the graphs that are moving their way down. So this is just kind of an introduction into our exponential growth and decay, but hopefully you're seeing the general pattern of the graph.